Hello everyone, can you hear me okay? Thanks for coming, my name is Alex, I'm a software engineer at Google and I actively use gRPC. And today we will talk about gRPC and how it can be beneficial for you and your project. And first of all, what is gRPC? As you know, in modern world, every client call results in hundreds remote network calls between microservices on your backend. And to make this inter-process communication efficient, Google developed its own framework for remote procedure calls, or RPCs, and it was called Stub. Stub was used inside the company for many years, and in 2015, Google introduced open source version of Stub, which was called gRPC. gRPC stands for gRPC Remote Procedure Call. It's built with all the scalability, performance, and API lessons learned from years of using Stub. Current version is 1.4.0, it's stable and production ready. Here you can ask why Google decided to reinvent the wheel. Why didn't it use some of the existing approaches like REST over HTTP, which is de facto standard in the industry today? Let's look at a simple example. Google Cloud PubSub team used to provide their client libraries built with JSON over HTTP. Last year, they released gRPC version of their client library. And their benchmarks demonstrated up to 11 times throughput improvement per CPU, just by switching their client library from JSON over HTTP to gRPC. You can say it's unfair to compare binary protocol with text protocol, and you will be right, it is unfair. But gRPC gives you this performance improvement out of the box. And talking about performance, you probably heard that Google is believed to handle billions of remote calls per second. But you know what? Now forget about it. Why would you care? You probably don't. Do you? Because what is important for you is how many requests per second or QPS you can handle, not Google does. When you split your monolith to multiple microservices, all those calls that used to be in process are remote now, and latency with throughput are kind of important. So, how many QPS you can handle? gRPC makes this question very easy to answer. gRPC team continuously running performance benchmarks. If you follow a link on the slide, you can find real-time performance dashboards for the latest available release and for the latest development version from master. You can see on this dashboard that with gRPC Java, you can achieve over 140,000 QPS on 8-core machines, or even more than 400,000 QPS if you use 32-core VMs. And actually, it's not the highest QPS you can achieve with gRPC, but we will talk about it a little bit later. What is important to understand that it's not something that was measured once and published. It is something that is measured for every single pull request. And for gRPC team, it helps to identify any performance regression as soon as possible. But for us, for gRPC users, it helps to understand what throughput and RPC latency we can achieve using gRPC. And when we upgrade, when we take a new version of gRPC, we always know what to expect. We know that performance was not degraded compared to the version we use. It gives you not only performance, it gives you predictable performance. And one of the main sources of gRPC performance is its network protocol. gRPC works over a new version of HTTP. HTTP2 or H2 is an evolution of speedy network protocol, originally developed by Google. It was designed to address some of the fundamental issues of HTTP1 or H1. For the sake of time, we will not deep dive into it today, but let me just highlight some of the main changes in H2. First of all, H2 is a binary protocol, unlike text H1. H2 can use single TCP connection for multiple HTTP connections that helps to increase parallelism. H2 addresses header-flag blocking that was an issue in H1. It has efficient header compression mechanism called HPEG that helps to reduce protocol overhead. And it has some other features like server push and stream prioritization. To demonstrate the difference between H1 and H2, we can go to sites like http2demo.io. And what you can see on the slide is the very same image divided into 180 tiles loaded by different versions of HTTP protocol. So gRPC uses HTTP2 as a transport protocol, because performance is a first-class citizen in gRPC. And performance is number one reason to use gRPC, but it's not the only reason. And we will talk about other reasons today as well, but now let's see how to use gRPC. Like many other RPC solutions, gRPC is built around the idea of defining your service and its method that can be called remotely. And default out-of-the-box interface definition language, or IDL, in gRPC is protobuf. Protobuf is an open-sourced binary serialization protocol and IDL from Google. Now let's see how a simple weather service looks like. We create a file called grpc.proto, and using protobuf version 3, we define an RPC method. Let's have an RPC method getCurrent. It takes weather request and returns weather response. And protobuf allows us to define some custom options, like what will be the Java package when we generate classes from it. Protobuf is available for multiple platforms, not only for Java. So you can define a contract of your service using language-agnostic definition. In fact, even gRPC itself is a payload-agnostic, so there can be other IDLs and serialization protocols, not only protobuf. You can implement your own implementation and plug it if you need. And today there are companies in the industry that already use gRPC not with protobuf, but with Thrift, for example. But standard out-of-the-box implementation from Google is based on protobuf. Now we have to define our request and response messages. Protobuf supports many standard data types and allows you to define your custom messages or structures. Our weather request will have a field coordinates with latitude and longitude. And weather response has temperature and humidity, whereas temperature is a message with degrees and units. When we define a field in protobuf, we have to specify its type, its name, and its number or index. This index will be used to encode the field into a binary format. We can even rename a field, and this change will be compatible as long as we keep the same index. So now we have service definition, which is a contract of our service, which is a common language between two services talking to each other, and we have to use gRPC runtime to generate classes from it. We can do it from command line, or we can use build system plugins. There are plugins available for Maven, for Gradle, for Bazel. After we run it, we see generated classes for all the messages we defined and builders for them. And we see weather service gRPC class. Inside this class, we can find service definition, which is an abstract implementation of our service, and methods to create client libraries or client stubs. Now, let's implement gRPC service. To implement gRPC service, we have to extend this generated abstract class and override its RPC method. In our case, it's getCurrent method. It takes weather request and stream observer of weather responses. And stream observer is one of the key interfaces in gRPC. It's used by both client and server for sending and receiving messages. It has three methods: onNext, onError, and onCompleted. When we want to send a response to our client, we call onNext with a response message. If we want to send an error, we call onError with an exception as an argument. And when we want to complete a stream, we call onCompleted. The simplest implementation will look like this. We use builder to create a response, we pass it to onNext, and we complete a stream using method onCompleted. Now we have to put the service into gRPC server. We use native server builder, we set port, we add our service, and we call start. Here we could add multiple services. For this purpose, we would call add service multiple times. Of course, there are many ways to configure gRPC server. You can add interceptors, you can add service discovery, load balancing, you can configure your thread pools, and so on. But this is the simplest possible standard configuration. Now server is ready, let's create some clients. It's pretty simple. We use native channel builder for address build, and we created a channel. And channel in gRPC is a logical abstraction that represents connection between your client and your service. In real life, you will most likely not create channel for host and port. You have service discovery, you have load balancing and other stuff, and gRPC has abstractions for all that. But let's keep it simple for now. Using channel, we can create libraries or stubs. Is anyone here like writing client libraries? You don't have to do it manually anymore. gRPC Java generates statically typed client libraries for you. There are 3 types of client libraries in gRPC. Async Client, you can create it with new Stub method. Blocking Client, you can build it with new block and Stub method. And Future-based Stub. Future-based Stub is an async client as well, but it has an API based on futures. And don't worry, in real life you will most likely only need one of them, not all 3. The simplest client to use is blocking client. For your weather service, it has method getCurrent. You send a request, you get a response. This code is easy to write and read, but it blocks the current thread. If you don't want to block the current thread, we can use async client. Async client takes a request and stream observer of the response. The stream observer has the very same stream method on next and completed and an error. When server sends us a response, we will get it in onNext method. If server sends an error, we will get an exception in onError method. And when stream is completed, onCompleted method will be called. What is important to understand here is that when we call client getCurrent, our current thread will not be blocked. It will continue its execution, and we can call other services or do something else from the very same thread. And when we have a response from server, onNext method will be called from another thread, not from the thread we sent our request from. This approach allows us to scale number of requests in flight beyond the number of threads in our worker thread pool. And that's everything we need. We wrote our server, we wrote our clients. Now you see client on the slide. Here you can see server again. But you will tell me, you know what? This is not very useful because it's not how you write your microservices. In real life, your microservices have what? Most likely, they have downstream dependencies. You call other microservices, you call data storage, you call other endpoints. Your weather service can call temperature service, humidity service, and wind service, and these services can call other services and so forth. Let's have service definitions for these services as well. The services will have getCurrent method, same as weather service. They take coordinates and return temperature, humidity, and wind. But hold on, our weather response didn't contain wind, did it? We need to add it. So we can easily add new field, it's wind, of type wind with index 3 to our response message. But what to do with our existing clients? Our existing clients that can be already deployed in some microservices or mobile clients that don't know anything about this new field. Will they all break? No, they won't, because in Protobuf 3, all the fields are optional. Your old clients, if they don't know about this field, they will just ignore it. They will not fail. They will fail later and for other reason, not due to gRPC. And this is how Protobuf and gRPC give you backwards compatibility. And now, let's see how our service will evolve. The simplest implementation we can think of, use blocking clients. We inject blocking clients for all 3 downstream services to our constructor. And then, in getCurrent method, we just call them one by one, build a response, and return a response to our client. It looks simple, but there is a problem in this code. It's sequential. We have only one outgoing request at a time, temperature, then humidity, then wind. Our latency is the sum of all 3 request latencies. It's slow and it blocks the current thread. When we block the current thread for a request, number of network calls our server can make is limited by the number of threads in our thread pool. But what if we want to scale, if we want to have more requests in flight? For this purpose, we can use non-blocking clients. We can use future stubs or async stubs. Let's do it with future stubs because we haven't seen how to use them yet. We inject them. And then, in getCurrent method, we send all 3 requests in parallel. When we call getCurrent on a future stub, it returns us Guava future. This future will be executed when a server has a response for us. Then we map this future using method future.transform. We transform a response from our downstream service to weather response. And again, it will be executed only when we have results. Same for all three downstream dependencies. Then we take all these three features and collect them into a single feature using method allasList. And this responses feature will be completed only when we have results from all three downstream calls. Now we have responses feature, and we have the callback. We have the callback on this responses feature, and when we have results from all three services, we send a result to our client. So what we did, we send three parallel requests, we collect their results when they're ready, and we send a response to our client with all these three results combined together. You can ask me, how could we send three parallel requests from a single execution thread? What thread will make these I/O calls? What threads will be waiting for an I/O? To answer this question, we have to go back and see how we created the stubs. We used Netty Channel Builder. And for server, we use Netty Server Builder. gRPC Java implementation is built on Netty. Netty is a network application framework that gives us asynchronous and non-blocking I/O. Netty has an abstraction called event loop. There is a thread that handles all I/O events in an endless loop. Number of these event loops is usually very small, and it's close to the number of available CPUs to your process. When a new message arrives from the network, event loop reads it, but it doesn't process the message itself. It submits it to worker executor, and the executor will process the message. When an executor wants to send some data to the network, it creates a message. It gives this message together with a callback to the event loop, and it doesn't wait for the response. Event loop writes the message to the network, and when it receives an asynchronous response from the network, it returns this response to the worker executor using provided callback. This approach of multiplexing connection on a single I/O thread allows us to decouple I/O from waiting threads, and it scales way much better than thread per I/O approach. If we go back to the service that we wrote, you could ask me, why do we need to call onCompleted after onNext? Doesn't onNext mean that we send the data to our client and stream can be closed? If it doesn't, can we call onNext multiple times before calling onCompleted? Let's see. A long time ago, even before REST and HTTP1 was invented, Heraclitus told people that everything flows. And it still does, because the world is not static. And weather changes, unfortunately. Temperature, humidity, and wind, they all change. And they change independently to some extent. What if we can subscribe to these changes rather than pull them? In gRPC, we can add stream modifier to the response, and we will get streaming services. Now, our services can send multiple responses to the same request. As soon as value changes, we can notify our client. But our request, our coordinates, is not static as well. We can change our location, and we want to be notified about the weather in our new location. So in gRPC, we can add stream modifier to the request as well. So now client can send the server an updated request or multiple requests. And we probably have to rename our methods, because technically they don't get current anymore. They're more observed now. So what do we have now? We have bidirectional streaming. Client can send multiple requests, and server can reply with multiple responses. And in general, there are 4 types of API in gRPC. Unary calls, one request, one response. Server streaming, when you have one request and multiple responses. Client streaming, when you have multiple requests and single response. And bidirectional streaming, multiple requests, multiple responses. So now, let me show you how to implement and run bidirectional streaming service. What we have here, we have weather streaming service that implements our bidirectional streaming API. First change, you see our RPC method, observe in this case, doesn't take a request as an argument anymore, but it returns stream observer of requests instead. When clients want to send some data, it can call onNext method on this stream observer, and this way it can send multiple requests calling onNext multiple times. For all three downstream services, we have streaming stubs. We inject them to our constructor, and then in observe method, what we do with stubs, we call observe method with stream observer of responses. Inside stream observer, what we do, we just convert the responses to weather responses and send them back to our client. When we want to send some requests to our downstream services, we have to call onNext method on stream observer that observe method returns us. And this is how we do it. We return stream observer of the requests to our client, and when client sends us a message, we will get this message in onNext method. When we get a message, we just send this request to all three downstream services. And when client completes the stream, we complete all these three streams. Now, let's try to run it. Our temperature, humidity, and wind service with some random delay will generate some random values for temperature, humidity, and wind. Oh, build failed because it could not. Sorry? I should be. Let's check. Okay. Oh, you're right, I'm not. It should not be on interview guest, right? It should be on conference instead. Okay. So now you see that it's not recorded. It's not recorded video. I actually do it. Okay. So yeah, now we have our streaming service, and we have streaming client as well. What we do in streaming client, we create channel, we create stub, and we call observe method on the stub. We provide stream observer weather responses to observe method, and when we get a response from our server, we will get it on next method. What we do here, we just print it to standard output stream with async client on next prefix. Now, let's try to run it. What we should see here is that weather service should send or stream us results. It doesn't, but okay, now it does. So what we see here is that our streaming server streams us back some results for humidity, temperature, and wind. Now I'll go back to our slides. Why is there no slides? Okay. And you can ask me, do you even need streaming? Most likely you do, because the world is not static. Use cases can include messaging application, real-time leaderboards, sport results, market quotes, data from your smart home devices, and many, many more. Think about your project. Most likely, you have use cases for streaming in your project. And what is also good about streaming is its performance. Performance for streaming calls is even better than for Unary because it's much less overhead. As of yesterday, not yesterday, but 3 days ago, sorry, for streaming RPCs, we can achieve over 500,000 QPS on 8-core machines, or even more than 1.5 million QPS if you use 32-core VMs. And what you see here is that it's not only Java. We see C++, we see Go, And yes, gRPC supports at least 10 programming languages on 5 platforms. gRPC will generate service definitions and client stubs that can be used in all these languages. What it gives your team more freedom and flexibility. You can write prototype of your service in Python and then rewrite it for production in Go. And your clients will not even know. Their client libraries will not change at all as long as you implement the same IDL. You can think that with throughput of million QPS, we can have as many microservices as we want, right? Every single call now can be remote. But now, we have to think about fault tolerance, because network issues are not limited to latency and bandwidth. When we split our monolith to multiple microservices, we significantly increase the number of network calls. And every network call is an integration point anyway, even if it's blazingly fast. And integration points are considered to be #1 killer of software systems. When we design and build a service that interacts with other services, our job is not to eliminate every possible source of failure simply because it's impossible. Our job is to be able to protect our service from these failures. It's not if failure happens, it's when it happens. And to be able to protect our service, we should follow some simple rules and techniques, and today we'll talk about some of them. First of all, it's very obvious rule: use timeouts. Use timeouts for every integration point of your application. Timeouts isolate failures and help us to protect our service from other services' failures. This advice is very obvious, but using timeouts properly is not as easy as it sounds. Let's say our client calls gateway service, which is blue on the slide, with timeout of 200 milliseconds. And blue service makes 3 network calls, and these services call other services and more services down the stack. What timeout should we use for these calls? The simplest way is just to apply the default timeout for all network calls. Will it work? Well, if all our downstream services are fast and latency is low, it will. Here you see total timeout of 130 milliseconds, but we need timeouts not when everything is great and fast. We need timeouts when something is wrong. Let's see what can happen if not all of our services are that fast. We have our client call with 200 milliseconds timeout, and it takes 30 milliseconds to call the first service, 80 to call the second, and 100 more milliseconds to call the third one. What happens? It's 210 milliseconds total. Timeout on our client exceeded. Our services have not even started to reply, but our client and our gateway, they're not waiting for the response anymore. But our services are still working because they have this default timeout of 200 milliseconds for every RPC call. What happens when client receives a timeout? Most likely, it will retry. But remember, our services, they're still doing this useless processing of the old request, and now they have even less resources to process new requests. And if retry fails, client can retry again and again. And these retries can overload the system and lead to cascading failures, even if we use timeouts. So default timeouts are probably not the best idea. What can we use instead? What about trying to tune timeouts for every service call? But what should be these values? We can try to simply decrease this value down the stack. Let's say if client timeout is 200 milliseconds, we can give the first call in this chain 190, the second 110, and the last 50 milliseconds. Sounds reasonable? Let's see. We have those predefined custom timeouts, and service and client timeout is still 200 milliseconds. Let's assume the first request took 30 milliseconds, second 80, and third one 25 milliseconds, and the last service replies in 30 milliseconds. So for the last service, we have 55 milliseconds round trip. We already reached custom timeout of 50 milliseconds. RPC failed. Despite the fact that our client can still wait for the response. Now we have to return our client some error, even though the client timeout of 200 milliseconds is not reached yet. Going back to the original question, how should we distribute timeouts? And what makes it even worse, that in real life our call topology is not that simple. in the real world, it can be something like that. And we don't know in advance how. And we made another assumption. We assume that we know what our client timeout would be. But oftentimes we don't. Different clients of our service can make their requests with different timeouts. How should we distribute these timeouts? As we saw, none of the strategies were good. So let's see how gRPC solves this problem. How timeouts are implemented in gRPC. They're not. gRPC Java doesn't support timeouts, but gRPC supports deadlines instead. If we want to specify a deadline for our RPC, we can call this deadline after on client Stub. Calling this deadline after 200 milliseconds get current will make a call with 200 milliseconds timeout or deadline. But what is a deadline? Deadline is a fixed point in time by which our client is interested in the response. And if this point in time is reached, all RPCs for this request will be closed with deadline exceeded status code. Let's see how it works. Our client makes a request with deadline after 200 milliseconds. If current time is 0, deadline will be set to 200 milliseconds, and remaining deadline of 200 milliseconds will be sent in request metadata together with the request. If our gateway spends 60 milliseconds to process the request, when it makes an outgoing call to the read service, current time is 060, deadline is still 200, and remaining time is 140 milliseconds. It's sent again in request metadata. And if it took 90 milliseconds, and if next call took 90 milliseconds, when read service makes an outgoing request, the current time is 150 now, deadline 200, remaining time 50 milliseconds. Then yellow service processes the call in 60 milliseconds, and now yellow service is ready to call the green one, but the current time is 210 already. And deadline is still 200. Our client told us it would not wait more than until 200 milliseconds. At this point, gRPC will automatically fail all the calls for this request with deadline exceeded status code. And it won't even try to call the last service because it knows that nobody is waiting for this response anymore. Our service is happy, our system is idle, and we're ready to process new requests. This is exactly what we wanted, and we get it absolutely for free. When we make gRPC call with some deadline, this deadline will automatically be propagated for all downstream calls, no matter how many RPCs we have for this request. And when the deadline is exceeded, all RPCs will fail. And even more, on server side or receiver side, we can check how much time we have until deadline. If we have a database call or outgoing REST call, we have to apply some timeout for this calls because this calls integration points as well. What should be the timeouts for these calls? We can check how much time our gRPC client is going to wait and use this value as a timeout for database call, for example. And we can even subscribe to Cancellation, to Deadline, and perform some cleanup or finish some background task when client is not waiting anymore. There is a method called run expiration for this purpose. If deadline timeout is something we expect more or less, what we should do if our call was unexpectedly cancelled? User pressed cancel button, or client application crashed, or user lost internet connection. There are plenty of reasons for the request to be cancelled. A request to our service often results in multiple RPCs to other services. And if our client cancels the request, we don't want to keep all these downstream RPCs active. We want our client call cancellation to be resulted in outgoing call cancellation for the same request. This is called cancellation propagation. And gRPC gives it to you out of the box, absolutely for free. You don't have to specify anything when your incoming gRPC call is cancelled. All outgoing gRPC calls made from the context of this call will be cancelled automatically. They all will fail with cancel status code. And server always knows if the request is valid. And we can access this cancellation status. In fact, our stream observer provides us more than 3 methods on next and completed in an error. If we need additional methods, we can cast it to server call stream observer, and we will get some additional methods like isCancelled. isCancelled returns true if our client already cancels the request. The CPI allows us to subscribe to cancellation as well, and we can clean up some resources, cancel non-gRPC calls, stop calculations, and do something else when request is cancelled. One way to do it. Every gRPC call has a gRPC context associated with it. We can get it by calling context.current. gRPC context contains all these deadlines, cancellation statuses, cancellation causes, and it can also contain some custom values. We can write values to context and get values from it. And it allows us to subscribe to cancellation as well. Cancellations and deadlines help us to prevent catastrophic failures when something bad already happened. But can we have even more control? Probably even before something bad happens. Let's see what can happen if we have bidirectional streaming and the server produces much more data than client can consume. Client sends a request, and server has a lot of responses. It sends them all back to our client, and client is not able to process them all, it fails. Stream will be closed, and server will receive an error. On the other hand, client can send much more data than server is able to process. If server is slower than the client sends a request, server sends back a response, and client can send multiple responses to our server. If server is not able to process them all, it can fail. And now client receives cancelled, unavailable, or some other error. To avoid this kind of failures, we want both client and server to be able to negotiate how many requests each side can handle. It's called flow control. If client knows how many responses it can receive, it can ask server to send this number of responses and not more. If client has a request, it can send this request together with the number of responses it can handle, for example, 4, and server can send these 4 messages back if it has them. And then client can ask for 2 more messages, and server can send 2 more responses back. And both sides are healthy and happy. Same thing can be done in other direction. Server can tell a client how many requests it can process, and client can send up to this number of requests and not more. And everyone is happy again. And of course, with bidirectional streaming, you can have client and server-side flow control at the very same time. gRPC supports both client and server-side flow control. On this example, can I hold the question until the end of the talk? Thank you. On this example, we can see client-side flow control. Let me explain it. First of all, when we need flow control, we call observe method not with simple stream observer, but with its sub-interface, client call stream observer. This interface extends stream observer to add one additional method before start. This method will be called before the start of a call. And its argument is a client call stream observer for the outbound stream. Inside this method, we can call disable auto-inbound flow control on the outbound stream. And if we do it, we enable manual flow control. Now we have to tell our server when we are ready to receive messages and how many messages we can process. We can do it using request method of call stream observer. When we call request stream at the very bottom of the slide, we ask our server to send us up to 3 messages. And when we receive these 3 messages, we process them within the same method on next as before. That was the client side of flow control. On server side, we also need more than 3 methods on next, on completed, and on error. That's why we can cast our stream observer to server call stream observer. Server call stream observer gives us additional methods, including methods flow control. We can call setOnReady handler, give it a lambda expression, and this lambda will be called every time client is ready to receive a response. And we send a response from this method. We just don't send a response immediately to our client, we send a response when client is ready. That was client-side flow control. For the sake of time, I will demonstrate server-side flow control. It is very similar to client-side. So flow control helps us to balance producer and consumer, client and server. gRPC supports both client and server-side flow control. Manual flow control is disabled by default. We can enable it when we need it and when we know what we are doing. What else should we remember when we decided to split the monolith? Some of the things were much easier to do before we switched to microservices. Let's see how gRPC helps to approach some of these challenges. With microservices, we need to wait to discover our services. And even more, we usually have multiple instances of the same service. We have to choose what instance to call. And this is where we need service discovery and load balancing. gRPC allows us to plug strategies for both service discovery and load balancing into our channel. And on high level, we still work with client stubs as before. Our client stubs that don't know anything about service discovery load balancing. Channel does it. Remember I told you that channel is a logical abstraction between client and service. So on service, we usually have multiple servers, but we still work with one single channel and one single stub. When we create a channel, we can provide name resolval factory and load balancing factory, and gRPC will do the rest. gRPC has some simple default implementation ready for us, but if we need to customize the way we discover our services or balance our load, we can always write our own implementations. One more challenge we will face is how to test this farm. We need a way to exercise all these dependencies without relying on network communication. Network adds latency and unpredictability to our test. And even more, what used to be synchronous is async now, and we need a tooling to simplify testing. So gRPC provides us testing tools out of the box. It gives us classes for testing streams, for testing metadata, and more utility functions for unit and integration testing. And one of the most interesting and useful tools for testing in gRPC is InProcess transport. It's fully functional transport with all the features, but it doesn't create real network connection. So in our test, we create InProcess server using InProcess server builder instead of native server builder, and InProcess channel instead of native channel. But we use it as a real channel. Now test can make gRPC calls without real network communication. So now test can include RPC interactions but be fast and reliable at the very same time. And if you use JUnit, there is even JUnit rule that starts InProcess server, so it makes it even simpler to use. And there are much more features which we didn't have to cover, we didn't have time to cover today. For example, integration with distributed tracing system like Zipkin, Brave, OpenTracing that helps you to trace your request flow. There are interceptors for adding some cross-cutting behaviors. There are integrations with monitoring systems, authentication, and many, many more. And today there are many companies in the industry that already use gRPC. You can see some of them on the slide. It's not all just some of them. And your company logo can be here as well. As gRPC is designed to be pluggable and customizable, there are other companies and developers that contribute to gRPC ecosystem. And we want you to contribute as well. You can check out gRPC ecosystem GitHub repository and make gRPC even better. Please try it out, check gRPC website, clone gRPC repository. You can check out gRPC GitHub repository with gRPC demo examples that I showed you today. gRPC-IO Google group is one of the best ways to reach gRPC developers and users and ask your questions. And don't hesitate to contribute if you find it useful. To summarize what have been said, gRPC is a high-performance RPC framework originally developed by Google. It gives you bidirectional streaming with multiplexing over one single TCP connection. It's built on top of native that gives us asynchronous and unblocking I/O. It supports deadline and cancellation propagation out of the box. It gives us flow control It has pluggable service discovery and load balancing. It generates statically typed client libraries for you. It's available in at least 10 programming languages. It's stable, production ready, and has growing ecosystem. And thank you for being here today. I hope it was helpful. And now I will be happy to answer your questions.
Thank you very much. Very cool technology. Thank you so much. You could have flow control. Could you specify that in kilobytes per second or something like that instead of a number of hours?
If the question was, can you specify flow control window in kilobytes instead of messages? You cannot do it with gRPC. You can go one level below and do it on Netty. Netty gives you this power specifying your flow control window. Sure. Yes. So again, you can specify it in Netty, and I believe when you configure your gRPC client, there is even a way to specify a flow control window. But if you work on higher level of abstractions with gRPC messages, you just specify send me 3 messages, 5 messages. Yes, I am. Okay. So the question was, is gRPC compatible with Stream APIs? And if it's not, are there plans to do it? It's not compatible. First of all. Second, in gRPC ecosystem, I believe there are some attempts to do it already. So as far as I know, Google doesn't have any plans to provide standard implementation as for now. Because when gRPC, again, gRPC is an open source version of Stub. Stub was built on internal APIs. Right? When Google decided to open source Stub, there were discussions how we what an API should be. Should we use some of the existing APIs like RxJava, for example? And it was decided that we will not go with RxJava or any other third-party implementation just because Google didn't want to be dependent on third-party library. But in gRPC ecosystem, I believe there are some attempts already, and you can do it if you want. Yeah, okay. Yeah, the question was, how do you work in real life with thread safety without writing all the logs? So in real life, usually you have number of stream observers already written for you, or already written in your organization or in your team, right? If you need this kind of synchronized thread safe stream observer, you just take one of the existing stream observers. But yeah, there is no standard implementation for it. Because again, onNext method can be called from any other thread. Any other question? Okay, thank you for being here today.